Here we're going to look at how to solve problems as we look at orographic features that are going to affect how a parcel of air with a given temperature and relative humidity, how they're going to rise at the dry adiabatic lapse rate. They're going to condense into forming clouds. They're going to condense out any excess water vapor in the form of precipitation. And this will continue cooling as it rises at the wet adiabatic lapse rate. Then as it travels over the top of the mountain or the barrier onto the leeward side, it's going to fall or descend, compressing the air, heating it onto a plateau, and we will have different conditions over here. So if we look through the three phases here, we're really looking at the dimensions or the dynamics of what's taking place on some parcel of air with given information. So example 1. The question is, well, what is the air's capacity at sea level? So it's going to be referring to this picture here. So if you have access to this, you can always print it off. You can do whatever you need to do. The questions are, what is the air's capacity at sea level? Well, if I use 8-2, at 25 degrees C, air can hold 20 grams per kilogram. But number 2 reads, well, what is the water vapor content at sea level? Well, my water vapor content is going to be 20 grams per kilogram, and it's got a 50% relative humidity. So 50% of 20 grams per kilogram tells me that it's holding 10 grams per kilogram of water. And I'm simply basing it off of the numbers that are here in the picture. So now, what is the dew point temperature at sea level? Well, if it's holding 10 grams of water vapor, this is the capacity or the dew point of 15 degrees Celsius. So I can then use the 8-2 to then further make sense of it, right? In this case here, 10 grams per kilogram is the capacity at 15 degrees C. So really 8-2 is the lifeline of what it is you're using and trying to solve here for. So number 4, what is the elevation, or at what elevation does air at sea level reach its dew point? Well, it has to rise. As it rises, it's going to cool. It's going to cool at the dry adiabatic lapse rate, which is 10 degrees Celsius per 1,000 meters, which is 1 kilometer. Air will reach its dew point after it has ascended 1,000 meters. In other words, it's going to go from 25 degrees C to 15 degrees C. So in that, it travels 1,000 meters upward. So what elevation? 1,000 meters. So what elevation would clouds start to form? Well, clouds will start to form at this very line that we call the cloud line at 1,000 meters or 1 kilometer. So this is called the cloud line because the moisture in the air has reached saturation capacity, or a better way of saying it is its dew point. So what's going to be the temperature of the rising air at the summit of the mountain? So we're already 1,000 meters up the mountain. If we're 1,000 meters up the mountain, right, the summit is 5,000 meters total. So the air has to cool at the wet adiabatic lapse rate, or 5 degrees per 1,000 meters, for the next 4,000 meters. So that means it's going to cool another 20 degrees Celsius. So it's going to go from 15 degrees C, it's going to cool 20 degrees. So 15 minus 20 is going to reach negative 5 degrees Celsius at the summit, and that's up here. Next, how much water vapor will be condensed out of the rising air at the summit? Well, air at negative 5 degrees C can only hold 2.5 grams per kilogram. So we get this value when we look at 8-2. Right? We hold a value, and if you use your graph, you get a better value in here. And you'll see that we get this value that we're associating at about 2.5 grams per kilogram. But we started with 10 grams per kilogram, right? That's how much we had in the air. That's what we solved for number 2. So the air must have precipitated out, condensed out 7.5 grams per kilogram. So how much water vapor was condensed out? Well, 7.5 grams of original water was condensed out. So what's going to happen to the temperature of the descending air? Well, it will warm up. But if you write that, I'm going to count that completely wrong, because it will warm up at the dry adiabatic lapse rate, which is 10 degrees C per 1,000 meters. It falls and heats up due to the compression of air molecules. So when I look at this leeward side as it falls, it's heating up at the dry adiabatic lapse rate. So what's going to be the temperature when the air reaches 2,000 meters plateau on the leeward side? Well, air is going to descend it's going to heat up at the dry adiabatic lapse rate. So at 10 degrees C per 1,000 meters, it's going to fall or descend from 5,000 to 3,000 meters. Oh, excuse me, it's going to fall from 5,000 to 2,000 meters, which means it's descending 3,000 meters. Excuse me. So it will heat up 30 degrees, but it increases 30 degrees from -5 degrees. It's -5 degrees at the summit, which I calculated prior here, number 7. So it's going to reach 25 degrees Celsius. So the temperature of the air on the plateau is 25 degrees Celsius. So what's going to be the relative humidity on the leeward side at 2,000 meters? Well, okay, the air has 2.5 grams per kilogram. We calculated that because it's holding 2.5 grams per kilogram, but it lost 7.5 grams per kilogram of its original 10 grams that it had originally, right, at sea level. So it only has 2.5 left. So if the air has 2.5 left, and it's now at 25 degrees C, 25 degrees C now can hold, we can look that up, 25 grams per 25 degrees C can hold 20 grams per kilogram. I'm using 8-2 once again. That 2.5 divided by 20 tells me that it's about 12.5, or we'll call the relative humidity 13%. So why is the rain shadow desert commonly found on mountains on the leeward side? Well, the desert reflects warmer and drier conditions of air. Any moisture on the ground is quickly heated and evaporated into warmer, drier desert air. Now, I'm going to go through this next problem. I'm going to do a second one for you. These are practice problems on the website, that these are loaded in the PowerPoints. You can access the PowerPoints. I think you want to have a hard copy in front of you to do this. I'm going to go through this one a little bit quicker. I changed the values. I've got 23 degrees Celsius. I've got at sea level, I just changed my numbers here. I've got a relative humidity of 61%. The summit is 5.4 kilometers, or 5,400 meters. And the leeward plateau is 3.2 kilometers, or 3,200 meters. So we're going to go through the same set of questions here very quickly. And I'll flash it here so you can see this. Key to problems number 2. I've named this one problem number 2. What's the air's capacity at sea level? Well, its starting temperature is 23 degrees C. It holds about 17 grams per kilogram. What is the water vapor content at sea level? Water vapor content, 17 grams. Its capacity, it's only 61%. It was in my original information. Tells me it holds about 10.4 grams per kilogram. What is the dew point temperature at sea level? The temperature of air at sea level, if it's holding 10.4 grams, its capacity, right? If that's its capacity, then it's roughly 15 degrees Celsius. So what elevation will the air reach its dew point? Well, it's changing. Its air is rising. It's cooling. I should change that to cooling. It is cooling at the dry adiabatic lapse rate, right? It's cooling here, a dry adiabatic lapse rate, until it reaches, what is that? Should be about 800 meters. Yep, 0.8 kilometers. It goes from 25 to 15 degrees, right? That's its dew point. So that's 8 degrees. It's going to travel 8 degrees. It's going to travel 800 meters to cool 8 degrees. So what elevation will clouds start to form? Well, that's your 800 meters. This is your cloud line. So what will be the temperature of the rising air at the summit? Well, it's got to go from 800 meters to 5,400 meters, right? That was your new summit value, summit. Let's see. So the temperature of the rising at the summit, it's got to rise 4,600 meters, or 4.6 kilometers, and it's going to cool at the wet adiabatic lapse rate, which is 5 degrees per 1,000 meters. So it's going to decrease another 23 degrees, so it travels from 15. It loses 23 degrees, so I get a value of -8 degrees Celsius. So how much water can be condensed out, or will be condensed out? Well, remember, it started off with 10.4. And now it's at -8 degrees. It can only hold 2.3 grams per kilogram, right? At -8, holds a lot less, colder air. So from 10.4 minus 2.3, I get 8.1 grams per kilogram of water vapor that was condensed out in the form of precipitation. So what's going to happen to the temperature of the descending air? It's going to increase at the dry adiabatic lapse rate of 10 degrees Celsius per 1,000 meters. So what's going to be the air's temperature when it reaches the 3.2 kilometer plateau? 3.2 kilometers is 3,200 meters, right? So we're up here and now we're descending. So it's got to go from 5,400 to 3,200. It fell or descended 2.2 kilometers, 2,200 meters. It increased at 10 degrees per 1,000 meters. So it increased in temperature 22 degrees. It went from -8 plus 22. It went to a value of 14 degrees Celsius. So what's going to be the relative humidity on the leeward side at 3.2 kilometers? Well, at 14 degrees, its capacity is 9 grams per kilogram. But remember, I only had 2.3 grams per kilogram. When I look up here at number 7, it can only hold 2.3 grams per kilogram. It precipitated everything else out, right? It precipitated 8.1 grams out, so it only has 2.3 grams per kilogram. So 2.3 divided by 9, where am I at? Right here, tells me its relative humidity is 26%. And the rain shadow desert is a result of descending warm air is going to be drier. It's going to evaporate any moisture available. And there are 2 talk-throughs of the practice problems from what we're doing in class.